Can you see me? Hello?
Yeah, we can see you.
Oh,
Hello, hello.
sorry. It seemed to not be working. Okay, I'm sorry. I've been dreading this because I've only missed, I think, one lecture so far this year with my undergraduates here in UCD because the network didn't work or my computer didn't work. So I've been dreading something like this would happen. Okay, so hold on a second now. Let me just open this up and we can start, okay? Let me see. Okay. Can you see me here?
Yep.
Okay, very good. And listen, the YouTube videos are how is that coming along?
Today in the morning, Maxim asked about that to the guys who are responsible for that in the ITMO University. So if I'm not mistaken, they hasn't answered yet because it was like maybe 2 hours ago.
Okay.
So yeah, but still we have all the recordings. So if there will be some troubles, we will upload them until the 4th of December.
Thank you. Again, that would be good because again, just for I know the students, sometimes they like to look at these things. I won't say immediately afterwards, but let's say within a day or so, just to refresh their mind. Okay, ladies and gentlemen.
And Professor Sheridan, here is one question from me.
Yeah.
Am I right that this is the last lecture from you, or we have some more lectures?
Oh, we have some more lectures. So I have at least on Friday. Yeah.
We have at least we have Friday, but we thinking about that to make it as a consultation. So I guess after today's lecture we will discuss that in 5 minutes if you have.
Okay. No, sorry, I had understood that the Saturday we had also put in for a lecture on the Saturday, and that the Saturday would be the consultation. No, I'm easy. I mean, I can lecture tomorrow as well if you like. I mean, it's very flexible for me, but I certainly need at least today and then one more lecture.
Okay.
Talk about
okay.
the polymer.
Then let us discuss it in the end of this lecture. Okay.
Okay. That's very good.
Okay.
Okay. So we stopped. The last day was lecture number 8. Okay. And so now we're talking about we're going to talk a little bit more about these polymers and polymer models. And again, as I said to you, I'm going to try and talk about things that are fairly settled and reasonably accepted. And what I'd hoped today was to talk about, let's say, the initial mathematical type models, and then go on from there to talk more about the material type models. So my last lecture will be more the material type models and also the consequences for things like holographic data storage. So things like the scaling law of diffraction that comes up in holographic data storage, and also scheduling, how you actually perform scheduling, the consequences of these models. Okay, so, and again, basically, just to remind you guys, and you guys in ITMO, I'm sure you're going to be organizing some sort of a celebration or something, but this next year is our 50th anniversary for Denis Zook's Nobel Prize. And then the year after is the 60th anniversary of the work of Denis Zook and Letha Newputnik. So the big days for us holography people. So let me just, maybe I can, sorry, excuse me. Maybe I can just do this way. No, excuse me, sorry. Just give me a second here. I'm really sorry. It's just
there is a close button on the upper right corner.
So the upper right corner.
Yeah.
Sorry, which one now?
That's.
You see, there's all these different versions. This one?
Yeah. No, under it.
Excuse me. I see.
Yeah, it's written on it. Close. Yeah. Maybe that's it.
Okay. Thank you. Oh. Thank you very much.
No problem.
Sorry, I have so many different versions of different types of software here that it's driving me mad, to be honest with you. And I had this unfortunate thing that because I combined some files that are older files together, I get some very strange effects. Let's put it like that. Okay, so basically, these are big days coming up. And again, just a quick run through of something we've done in the past, which was characterizing spatial light modulators. So basically we have an array. These were hollow eye. We've mostly worked with hollow eye, and hollow eye have amplitude and phase and mixed. And this was a situation where every pixel had a loss and phase shift associated with it. We were very interested in the polarization effects of these elements. And we were using them in optical systems for performing encryption, where we had two different spatial light modulators operating at the same time. And we looked at things like amplitude encryption and also polarization encryption, where each one of these gray levels actually corresponds to a different in polarization state. And so using this type of system, we could have two different types, two different patterns. You imply are imposing two different types of encryption, either amplitude, phase, or polarization. And we could come along and we could encrypt data and we could decrypt. So there's some examples here of the inputs, the image on one and the image on the second one, and then an output, and then how we could get around this. And we went certainly theoretically and looked at much more complicated arrangements. And this was the result of that. Okay, photopolymer materials. So again, I draw your attention to this roadmap, and I've been told that the final version is coming out in December this year, next week, hopefully. And it got a very nice overview from a lot of different places around the world. This is a sort of an overview of our literature, papers we've written and published. And again, I'll circulate this to everybody afterwards if they want. And it's sort of chronological order here. So the earliest ones to the later ones, and sort of how we had the evolution. And I'm hoping to kind of deal with most of these topics. I'm going to touch on most of these things, certainly before 2010 more detail than after 2010, but in the next couple of lectures, I'm going to look at these and the sort of things we've done. Again, sort of a potted history of actual photopolymer materials. So the very first work that was done by people were liquid suspensions of photopolymers. So these were materials where you shone light inside and you actually had the precipitation out. You had essentially the formation of heavier molecule chains. And if you waited long and switched the light off, you'd actually see deposits of polymer in the bottom of your receptacle. So in other words, you'd have a solution with the monomer suspended, you'd expose with the light, you'd form chains, and then basically, if you stop the light, eventually you'd actually see these polymer chains falling to the bottom of the thing that contained the liquid. But people went away and they did work in this area. And in fact, using holography for finding out things about chemical solutions, forming holographic gratings and probing those holographic gratings was an area of, and still is an area of work by a lot of people. Then people went and looked at solid type materials. And in that area, I'd probably talk about things like Close and Jenny, and also Calixto, who would have been the acrylamide person. We would have known the acrylamide, polyvinyl alcohol acrylamide, where acrylamide is a monomer and polyvinyl alcohol forms the matrix. And I'll talk a little bit about this. And people were interested in trying to model these solid layers. And there wasn't just this polyvinyl alcohol acrylamide. People also worked with PQ, PMMA, and the DuPont type material, crop type material, epoxy resin based materials, and ever more complicated types of forms of materials. They all have this basic operation that they absorb light. You produce a variation in the refractive index by varying some characteristic of the chemicals inside the layer. And we're going to talk primarily about what are called free radical materials, where you actually have an absorption producing a radical, which leads to a polymerization process. And I'll mention some of the materials probably more in the next lecture than in this lecture. Essentially, these photopolymers are an enabling technology. They're a material platform, and they permit the formation of things like hybrid optoelectronic circuits. So you can, at the crudest level, you can embed you can place sources and detectors and optoelectronic type equipment, and you can introduce this material often as a liquid or a solution, or you can start off with a hard layer and then implant your optoelectronics. And you can build hybrid optoelectronic circuits. And if I have time later, I'll also mention this notion of self-solitary waves, self-forming waves. And we'll talk about those. It's a nonlinear material, so it is a self-processing material, and this can lead to these production of self-written waveguides, self-focusing and spatial solitrons. You can produce diffractive and refractive optical elements. So I'm going to talk a little bit about refractive elements, but mostly diffractive elements. And in holography, of course, we've talked about 3D displays, metrology, and data storage. And in terms of data storage, just in terms of some highlights in relation to discussing materials and optimization materials. And again, I can supply references for all these things, but if you type in these with a star, you'll get something. Trentler, Suzuki was the first one that I'm aware of that introduced nanoparticles for counter diffusion. Huge amounts of work been done by Tomita. Read-write technologies. And again, you can also read about the very, very inspirational work of In-Phase Technologies, a company in America, a man called Bill Wilson. And performance to do with improving resolution of these materials, which include introducing counter-propagating materials, which enhance, for example, refractive index modulation, but also, in our case, with free radicals, introduction of chain transfer agents. Again, work that was further work done on this by Yasua, and if I've got time, I'm going to talk a little bit about this the next day. So, what are our aims here? What are we trying to do? We've talked a lot about the actual diffraction and the electromagnetic models associated with diffraction. Well, we want to understand the material response. And basically, we want to understand it so we can use the materials we have better. We can design and understand effects. And I'll show you how I use this to talk about scheduling. But also because we want to see if we can develop new polymer systems. So what are the things we can change in order to improve the performance of these systems? Procedure. Well, we're going to break the process taking place during exposure and post-exposure down into a set of sub-processes or steps. And we're going to extract as much quantitative information as possible for each sub-process. So if you'd like, even before we put those chemicals together, we're going to find out things about them, like, for example, what the refractive index of the individual components are, what the refractive index of the monomer is, and what the refractive index of the polymer is, etc., or the matrix. And then we're going to put them together, and then we're going to try and, for example, take a material in which we have no monomer, but we have dye, and try and find out some information about what happens if there's no free radical polymerization taking place. And so bit by bit, we're going to build up a whole series of, but through experimentation, we'll find a whole series of different types of information, and then we have to get a model where we can bring all these types of bits of information together. So we combine appropriately and test the model using reproducible experimental data sets, which is harder than people think. I mean, as you know, holography is quite a messy business. It's very, very hard to make over a series of months or years layers that are consistent and experiments that are consistent. Okay, so you've always got to be aware of that. So the steps. The first one we've already talked a bit about. We're going to measure and probe the holographic grating diffraction efficiency during formation and post-exposure. So we're going to be seeing what happens when we switch off the exposing beam. And we're going to look for dark reactions and also effects like shrinking and swelling. And we're going to use our optical measurements, our growth curves, and our angular scans. And primarily, we're going to use unslanted transmission gratings. And I'm going to talk a little bit about that. And mainly, we're going to do that because we want to avoid things to do with shrinking and swelling. Okay, gross effects due to shrinking and swelling. We want to apply electromagnetic models to extract refractive index modulation variation with time. So once we've got our intensities and we've got our diffraction efficiencies, we want to work back from those to modulations, so the actual refractive index modulation. And we might be interested in a single harmonic, so this N1, this change, the lowest harmonic, or we might be interested in a series of them. So we might have multiple grating components. And if we go to multiple grating components, we're going to have to use N-wave theory or rigorous electromagnetic theory. And we're also going to have to be very careful about things like surface relief structure. So we're going to apply the electromagnetic model to get back to the refractive index. And we're also then going to have to find out things about what's happening during the dye absorption, recovery, and bleaching. So what actually starts off the polymerization process? So as I said, we may take layers which have no monomer, yeah, or have no electron donor, and find out what happens, what processes happen in that case. So we can do absorption, recovery of the dye, bleaching of the dye, and also inhibition type effects that we might see in the formation of the grating. And then we've got to develop models and numerically fit predictions of these models to produce or predict the refractive index, given information about the refractive index of the individual components at the replay wavelength. So we've got a huge range of steps here, which goes all the way from understanding the photochemistry, understanding polymerization, which also depends on things like viscosity in the material, converting what we form in terms of the chemistry into refractive index, converting then going from refractive index to diffraction efficiency, and growth curves and angular scans. Okay, so it's multi tasking here and the languages of the different people. So for example, dye people are not polymer science people, and vice versa. So even within the chemistry, there's subgroups. So first of all, our experimental characterization. So again, we've talked about this. How does the diffraction efficiency vary with exposure dose? What do the experimental curves look like? Is overmodulation experimentally observed? Does shrinkage or swelling happen? How do we measure off-Bragg curves? How do they behave? How does the diffraction efficiency change as the period, spatial frequency of the exposing pattern changes? And that's going to be critical because that's going to tell us the maximum resolution, the smallest period we can actually record. And we want to quantitatively understand the material response, and can the response be improved? Can we vary the chemical composition? So we take a photosensitive layer. And basically that's going to, and we, as I said, we've picked this particular material because it's not very poisonous and because it's easy to work with, okay? So this is our basic material substance, and it's got a recipe. And again, you try to reproduce this recipe as a baseline because many other people have worked with it, so you can do a one-to-one comparison. And at the same time, you're also looking at varying the composition. So you take these mixtures and you may vary them to see what's the best mixture, okay? And then you add other chemicals, like, for example, as I mentioned, this chain transfer agent, or you may add some small particles like carbon nanotubes or titanium dioxide particles, so to produce some counter diffusion, okay? So you take a baseline and then you manipulate that. So we're going to, and why do we use chain transfer agents? Well, chain transfer agents, I'm going to discuss, are ways to actually control the length of these chains. And with the proposal we made to actually control the non-local parameter. So to control, because you're just spreading, if you'd like, during formation of the actual grating. We're going to talk about that. Okay, so here's our basic reaction. We've got an unslanted transmission grating being exposed here in red and being probed here, for example, in green. We expose, we fabricate, and we can use this process over here to rotate, so we can do the angular scans. And it's all run by LabVIEW, and so we can control exposure times, etc., or the position that's exposed. And it sounds a lot better than it is. It's actually a very crude way to do these things, but we have produced arrays, we have produced multiple datas on the same plate, producing the same data and multiple plates. And as I've shown you this curve before, we get a diffraction efficiency curve, which is down here. And if we overmodulate, we get something like this in an ideal case. We then take we can then use Kogelnick's theory to go from this to a growth curve of the refractive index. So these here would be functions of time. We can take an experimental curve, and here we again show the fall off in the grating strength post exposure. So if we stop exposing at some point over here, we get some growth and then we get a decay. And then we can come along and look at the off-Bragg response and see what happens to it as we have shrinking or swelling taking place during the actual recording or post-exposure. So we'll talk a little bit about that. So shrinking and swelling. If we have a nice unslanted grating, we get a nice sink-like variation, which looks like this, okay? So this will be an unslanted grating. Even if we have shrinking or swelling, the on-Bragg condition doesn't change that much, very, very little. And we have, in our material, if we do a nice exposure, so a nice, slow, steady exposure, we get ourselves very nice sink-like behavior here for off-Bragg angular replay. If we use a slanted grating, so this now would be, this is the thickness of the layer, and here we start off with a fringe which looks like this, so this is during exposure. If we have some shrinking or swelling, so swelling here basically happens essentially in this direction, so in the thickness direction of the layer. And if that happens, what we will see is that our fringes are going to move. So if we think of our K vector being perpendicular to these fringes, what's going to happen if we've got shrinking or swelling, in this case swelling, is that our K vector, the grating vector, is going to change orientation. So what was on Bragg is now going to be off Bragg. If we come and look at the corresponding angular burp, so this now is for an unslanted grating, and we see what happens over time, we'll see that if we start off, this is our original case here, and it's reasonably symmetric. Over time, what's going to happen is we're going to, first of all, get swelling. We get a swelling effect. So our Bragg response moves in this direction, yeah? So again, we're scanning, we're doing angular scans. These are separate angular scans, and they've taken place over a number of hours. And what will happen is we start off with something like this, and then over time, we're going to get some decrease. And sometimes this is quite rapid, relatively speaking, yeah? And then following that, we're actually going to get an increase. We're actually going to get this moving back So we get a swelling followed by some shrinkage. And the shrinkage then will take some time to achieve. And we can actually plot out the change in Bragg angle. So the angle here where we get the maximum diffraction efficiency over time. And we see here it moving to the left and then it moving back to the right again. And we can see that we get not very big, but some change in degrees here. We're talking here about starting off at about 0.2, coming down here to a minimum of minus 0.6, and then coming back up here again to about 0.4. So this is a dynamic situation. It's like a spring. We have some effect due to the densification, followed by some relaxation in the material as the materials redistribute themselves through diffusion. And we can also come along and find this using our models, our Kogelnik model, and tracking the off Bragg. We can come along and actually track what's happening with the height. So we get shrinkage followed by swelling. Yeah. Let's just have a look at this. Sorry, swelling followed by shrinkage. So it gets bigger and then it goes down and gets smaller again. So this expands and then comes back down again. So let's show an extreme situation of this. This is actually an experiment, a nice little experiment you can do, which is to focus a spot on your layer, on your holographic layer. And then you can use various techniques, optical or even contact methods, to look at your surface evolution. So here we have a sort of a stop. You start off initially and you've got a dip. This width here would be about, I think it was like hundreds of microns. There's an axis on here somewhere. So you start off with this immediately after exposure. You get some relaxation. You start getting a swelling, and there's a dip now around this. And eventually you get something like this. And you can go away and do the same thing on an array. And don't worry about these some errors here. But you can see here, you get this shrinking and a swelling. And this is actually quite rotund. You could imagine using something like this as refractive optical elements, but you've got to remember, you're going to have a change in your density actually below this. So you've got a combined effect of a volume change in density followed by the shrinking and swelling and the production of a surface relief pattern. So all materials, I don't think I've ever met any holographic recording material that doesn't exhibit this type of behavior. You've got to take account of it. And for example, if you've got a volume holographic grating, typically the period is quite small. If it's very, very small, then surface tension effects act to smooth out any perturbation on the surface. So the surface wants to be straight, wants to have the lowest energy possible. Introducing these sort of bumps and curves on the surface are going to increase the stress or strains, the tension in the surface. So bigger patterns like this, where you've got very large size, you get much more pronounced variation. For your fine gratings, typically because of surface tension effects, you don't get as strong a surface relief pattern. And for our material, it's about 100 microns. Once you go to size of structures or periods, about 100 microns, 50 microns, you begin to see appreciable diffraction effects due to perturbation on the surface. Okay. So again, we talked about growth curves, off-Bragg responses, overmodulation, yeah? And we also talked about this idea of the spatial frequency response. I'm going to talk a little bit more about this today. And the Covestro material having a very broad response, whereas the acrylamide material has a band pass. Covestro also rolls off over here at about 5,000 lines a millimeter, which is quite good. The best material I've heard reported, I think, was dichromated gelatin, and they were talking about appreciable, measurable, let's say, diffraction efficiencies being produced at 10,000 lines per millimeter, which is very good. Yeah, it's very, very good. Okay, so step B. So we've gone and we've been able to do our measurements, and we've been able to see all these different types of effects that are happening during the measurement. What are we going to do now? Well, we're going to apply our electromagnetic models, all the things we've been talking about before, to extract the refractive index modulation variation with time from the growth curves and from the angular scans. So that should be a U there. Apologies for that. So step B. So we're back to this model here. And we're basically going to be using Kogelnik. We've got a small period. We've checked out that we've got a thick grating. So we can start off with Kogelnik to get a first idea of what's happening. And then as necessary, we can go to a multi-wave, coupled wave, or we can go to a rigorous. And we can supplement also with the Fresnel reflection coefficients. And again, basically, what does this mean? Well, it means here that we measure our diffracted beam. Yeah, this replay diffracted beam. And again, this is a different wavelength to the exposing beam, so it doesn't interact with the actual material. It has no effect on the dye. You're not recording any grating with it. It is diffracted by the refractive index produced by these two exposing beams. So we have a time varying diffraction efficiency here, and this time varying diffraction efficiency will vary also when we switch off the exposing beams, and we can also rotate this here so we can also get some information about the angular scan, or we can use the transmission beam to find out information about the angular scan. Because of course, if we rotate this grating, we're not going to be coming out with a diffracted beam in this direction, but the transmission beam is always going to be coming in this single direction here. So what do? Well, we measure our diffraction efficiency, the diffracted light divided by the input light, and from Kogelnik we know that's equal to the sine squared this, pi times the thickness times n1, and we're now saying that this refractive index modulation is variance as a function of time, divided by the wavelength, divided by the cosine of the theta, the half angle between these two recording beams. And so we can bring this on the other side and say, given our diffraction efficiency, we take a square root of it, we take the arc sine of it, we multiply by the wavelength cosine theta, divide by pi times d, and we now have our n1, our first estimation of our refractive index modulation. And again, we have to be clear about our polarization, etc. So that's our first step. And then we go on and we use more rigorous theory if we have to. And we can do our automatic fitting as well. Step C, measure the layer transmittance to quantify dye absorption, recovery, and bleaching with time. So again, we've come up with sets of experiments. I mentioned, for example, where we leave out only maybe the electron donor, and we'll see what happens to the dye, and we'll switch this light on and off, uniform intensity, and we switch it on and off, and from that we're able to extract out information about the dye, the rates associated with the different operations. And I showed you this type of diagram before. Essentially, every one of these pathways has associated with it some chemical reaction or photochemical reaction and a rate equation. And here's our production of these bleached processes. And so in order to get from our dye exposed, our exposed dye all the way down here to a situation where we start growing polymer chains, we have to come up with a set of differential equations, and then we have to fit the predictions of those set of differential equations to a set of independent measurements on our dye, either using the single beam or coming back up here and finding out what happens to these two beams that are transmitted by this actual process here. And we see that there are some complicated reactions taking place here, and there's some complicated photochemistry. And again, we try to work to the simplest and most generic models as we can, but you still, because of the different systems involved, end up with very different types of processes. This is very much a free radical type process, but there are other processes and other types of dyes that behave very, very differently. But the technique we employ seems to be applicable across these different types of dye systems. And then step D, develop models and numerically fit predictions to experimental data to estimate the parameter values. So now we're getting further away from the thing we've measured. We've measured the growth curves. We've converted the growth curves here into modulations. We've had to understand our dye, the process by which we start the polymerization process, and then we feed this in here into a model which is going to be able to predict these refractive indices. And to predict the refractive indices, you've got to be able to predict what happens with the polymerization and how you go from a polymerization into a refractive index. So we've got 3 steps that I hope I'll get through at least 2 of those today. So the first one is photopolymerization-driven diffusion. So we have our interference pattern initiates polymerization. In exposed regions, the polymerization removes monomer. So we've got this thing made up. It's got a matrix, and it's got the monomer, and it's got a dye, and it's got some other chemicals in there. And essentially, we put light in, and and what happens is the dye absorbs that light. And where the light is bright, you have more excited dye molecules. And where you have dark bands, or where you've got less light, you have fewer. And the more of these radicals, these excited dye molecules, the greater the chance that you can produce a radical. And that radical can essentially cause the initiation, the start of the formation of polymer. And then the polymer chains grow. And what we assume is that wherever the light is high and wherever we're producing the radicals, that's where we produce the polymer. The polymer is produced where the light is highest. And we reflect this in how we describe the polymerization process. Now, once we've actually got the polymerization process started, we have to remember what polymerization involves. It involves the conversion of monomer into polymer. So it involves the removal of monomer. And if you've got bright regions where you've removed a lot of monomer and converted it into polymer, you now have less monomer than you do in the dark regions. And so you've got a gradient, a density gradient. You've got more monomer in the dark regions than in the bright regions. And so what happens is the monomer starts to diffuse from the dark regions into the bright regions. So if we have an interference pattern, let's say sinusoidal interference pattern, we can see that we'll have a high value, a high amount of monomer in the dark regions. So the concentration of monomer is going to be exactly out of phase with the concentration of polymer. Okay, so where polymer is low, monomer is going to be high. And where the light is, that's where the polymer is going to be high. That's where you're going to form the polymer. So you're going to get a process whereby this monomer diffuses from the dark regions into the bright regions. And this process of diffusion, of course, is going to be much slower than the process of polymerization. And there's certainly the process of absorption of light by the dye and the production of radicals, which is local. All that's going to happen at, let's say, with certain time constants. And those time constants are going to be faster than the time constants associated with the diffusion of the monomer. Okay, the monomer diffusion is going to take time, whereas the polymerization here we're going to assume is instantaneous. Okay, so that's model one. So let's have a diagram here. Let's have some diagrams and let's have some discussion. And here we're following what I call PDD. And we're talking a photopolymerization driven diffusion. So the photopolymerization takes place and that creates the gradient, which then drives the monomer diffusion. And the first people who looked at this were these guys, Zhao and Morales, to my knowledge anyways. And they were working with DuPont type material. And what they had was a situation, they talked about a situation where they had two beams coming in producing the following interference pattern. So that's intensity as a function of X. So here's our mathematical formula. And this V here is the visibility. If the two intensities of the two exposing beams are balanced, they're equal, then that V, that visibility will be equal to 1. So the fringe will go all the way from a maximum value to 0. So the exposure takes place and the medium to start off with is homogeneous. Okay, we have the exact same mixtures or concentration of all the chemicals everywhere. That's what we start with. And then what's going to happen? Well, the light comes in and we've got bright and we've got dark bands. And in the bright bands, we've got the formation of these polymer chains, which you basically get by sticking all of these monomers together into a long chain. And then you're going to have less monomer in these regions. And then you're going to have a higher concentration of monomer in these regions. And then the monomer is going to start to diffuse in. Now, if the process is ongoing, as you expose and you use up the monomer in here, and you do it slowly, there's enough time for monomer in these regions to diffuse into these regions and also be part of the process. So even though you've got no exposure, no removal of monomer in here, the process is driven in such a way that if you have a nice steady exposure and a nice steady use of the monomer, and you allow enough time for the monomer to move from the dark regions into the bright regions, you're going to be able to use up the monomer that's even in these dark regions. So as I said, a dynamic type process. So you end up then with a density variation. And as I said, if you've got a nice smooth process, the highest polymerization is going to be in the middle. And then you're going to have a drop off in the polymerization, the concentration of polymer. And in these dark bands in the very middle here, where this is 0, you'll have no polymer. And again, we're going to assume that this polymer, somehow or other, has got a higher average index than the index of the same amount of space containing the same amount of monomer. So what happens is we have an increase in the refractive index in these regions. Now, it may be possible, for example, that the polymer takes up less space than the equivalent amount of monomer because it's packed more closely together. In which case, we might also expect some variation in the height, the depth here. That's where you get your shrinking and swelling, and you may have an average change in the thickness due to an average variation across the material, or you may have localized changes if you've got a very strong polymerization process in here. You might also expect a nonlinear process. For example, if I have a very high intensity in the bright band, okay, very high, I'm going to very quickly use up all the monomer in the bright band, and there won't be enough time for the monomer to come from the dark bands into the bright bands, and therefore we'll end up with a flat region here. We won't have a nice smooth sinusoid. We'll get something which looks more like a rectangle with some edges. And as the monomer then slowly diffuses in, it's going to be very rapidly used up before it gets to the center. And so you even exacerbate it. You make it not have a single sinusoidal harmonic, but multiple harmonics. So the cross-sectional refractive index, or density, looks more like a square wave. And we'll see about this, what this means. So the photopolymerization driven diffusion model. So I want to talk about this because this is where I started. And basically they proposed a set of physical and mathematical models. It had very, very little to do with the chemistry. Very, very little to do with the chemistry. And so, you know, they simply dealt with parameters like U, which is the monomer concentration, and D, the rate of diffusion of monomer, and F, a rate of polymerization, so a rate of removal of U. And this F was related to the exposing intensity. So as I said, this exposing intensity drives the process. So what was assumed essentially was that this polymerization process was a constant times, a constant times the exposing intensity. And so you had a polymerization process, which was a function of X and T, the position in X and the time. And of course, we're assuming this whole thing is, you've got a two plane waves. So we got a nice sinusoidal variation. And we have a K vector here, which is 2 pi over a period, and we have an unslanted transmission grating. So our fringes are perpendicular to the two boundaries. And in terms of material properties here, the way in which we turn light into polymer, we simply have a kappa. So that we're assuming the polymerization rate is proportional to the intensity, okay? Now, in fact, using fairly straightforward maths, you can show that the polymerization must be at least proportional to the square root of this intensity, okay? But we'll talk about that in a small while. And our kappa is a constant. So in that type of situation, well-known type of situation, we have a governing equation. So if we ignore this part here, which is the driving part, okay, we have an equation which relates the rate of change of U, the partial derivative with respect to time, as being related to the partial derivative with respect to position of the rate of diffusion, which may also be a function of time and of position. So as we expose, and for example, in the bright regions, it becomes more dense, we could imagine our diffusion constant changing, and this is a diffusion constant of the monomer, changing depending on where the monomer is inside the layer. So where there's a lot of polymerization, it might be harder for the monomer to move. And then another first order. If we've got a constant diffusion, then that D value comes outside of it. There's no variation of the diffusion with respect to position. We can take this outside here, and we've got the first derivative with respect to time is equal to a diffusion constant times second derivative of this with respect to space. And again, this is very much tied in with this Fick's law, this nice linear idea that if you've got differences in concentration, it governs things like osmosis, it governs a whole different set of processes. And you should have seen an equation which looks something like this before. If you haven't, you can look it up. And what you'll see is if this is a constant, you get nice, very nice exponential decays, for example, in relation to the diffusion. But now what we've got is we've got something which is driving the diffusion. This is the driving function. We've got something which is saying, well, this equation works very well if, for example, we have a constant distribution. If the U x of t is not varying, that's one thing. If we start off with some concentration variation, we can find out how that concentration variation is going to settle down to a nice steady value. So for example, if we had a high monomer concentration somewhere in the layer and no dye, and we just waited long enough, the monomer would eventually distribute itself equally out throughout the layer. But now what happens is we start off with a uniform distribution of U, and then we drive it using this function. And that's going to lead to a variation in U over time, and also there may be some densification, and so we may have a variation of the diffusion constant, but with position and time. Now, if we look at this equation here, and we know that this function here is cosinusoidal, then as a very good first guess, and turns out to be very accurate, we can assume that because the driving function has this periodicity in X, then all of these functions, the monomer concentration and the diffusion constant, can also be written as Fourier series, and these Fourier series are going to have the same fundamental grating vector value. So we're saying here now that we're driving it with a cosinusoidal, and what we're going to get out is something which can be written as the cosine of kx plus the cosine of 2kx plus the cosine of 3kx, etc. Okay? And we've here got this situation where we say, well, let's include just 3 here. And in the diffusion constant, we're actually only going to include 1. We're just going to keep in 1 component. So effectively, we have the 0 value, the DC or average value, the DC or average value. And then we're going to have some perturbation. And in fact, in many cases, we're not going to even worry about having m equal to 1. We're just going to assume that we've got the D0, an average value. We're going to assume the diffusion changes very, very little. okay? Or we're going to assume that we have an average value, and the average value will vary with time. It gets slightly denser as we go forward with time. So we substitute these in here, and then we look and see what the individual amplitudes are going to give us, the relationship between the different amplitudes. Now, I like this very much. I like it very much because, well, first of all, I could start off with the João Morales paper, and it always helps an awful lot if somebody else has already done some of the work, yeah? But the other reason I like this, and this should remind you very much of what Kogelnik did, yeah? He had amplitudes and he had components. He approximated the field using this sort of an expansion. It turns out the mathematics in this case is easier than the mathematics Kogelnik did, or the N-wave, coupled wave people did, because these are concentrations. These are concentrations. They're real valued. They're not complex valued. When we were dealing with fields, these things had to be complex valued. So it turns out that these types of the maths associated with this, that solving these equations is much easier because all of these things are real valued. You don't have interference effects, okay? So we substitute these into this and we get a set of coupled first order differential equations. Okay, in this case, again, I've only kept 2, but we could keep 3, or we could keep as many as we want. And the more we keep, the more accurate our results should be. And what we see is that we have a coupling between the zero harmonic, the average monomer concentration, and the first harmonic. Okay, so we're describing now, we started off with something where we had just a U0 and it was uniform everywhere. And now as we change the exposing intensity, yeah, and as we change the time, what we're going to see is, we'll increase the dose, we're going to see that we can describe what's happening to the monomer using this equation here. And we see now that the first harmonic, the first amplitude harmonic of this Fourier series, is related to the zeroth, yeah, itself, and it's also related to the second harmonic, yeah? And it's related by a series of this zeta, and it said this zeta is going to be F0 times the time, which is kappa, this material constant, times I0 times the time. So it's giving you information about the dose, the effective dose that's driving this material. And similarly, we have this R parameter, and this R parameter comes out of the mathematics, and it's a diffusion constant times k squared, which is k again, 2 pi over the period, divided by F0. It turns out it's dimensionless. Okay, and it's very important when you're talking about what governs the behavior. And the visibility is here. Again, if we change the visibility, just put it equal to 1, all these things become a half. And we do notice one here, where we've got this hyperbolic sine and hyperbolic cosine here, and they come out when we discuss the actual diffusion constant. There's an alpha here, which is associated with variations of the diffusion constant. It's but I'm not going to talk a lot about that. But just to note that we can allow for the diffusion constant to vary with time. Now, again, we've got to recall what this F is. This F is the rate of removal of the polymerization. Okay, it's telling us how much polymerization is taking place. So we can use this term here. We can use this term here, and specifically, we can integrate this over time, yeah, to find out how much polymer is formed. So given a certain amount of monomer at a particular time and position, and given the particular rate of removal of the polymer at that time, we can find at any given time the amount of monomer that's being converted into polymer. And if we integrate this over time, we're going to find the total amount of polymer at a position X for all the time. So you can integrate from time is equal to 0 up to some time, and that will give you the concentration of polymer. And we can write the concentration of polymer also as a Fourier series. So we have the concentration at any point in time will be equal to a sum of some amplitudes times these cosines. And if we do that, we can actually come along and we can integrate N0 is going to be equal to that. That's the DC, the average change in polymerization concentration. And N1 is the first harmonic. And we see that's equal to an integral over time, but we're using this zeta now, yeah, which has got the intensity built into it, again, of U0 and U1 and even U2, okay? So the contributions to the average permittivity, polymer concentration, come from not only the 0th order, the average monomer, but also the first monomer concentration. And the harmonic, yeah, this density variation due to the polymer here, is going to arise due to the 0, the 1, and the 2. They all make contributions to the actual polymer concentration formed. And this alpha, as I said, the rate of the U0 and U1, the first 2 monomer concentrations. And N0 and N1 are the first 2 polymer concentrations. So now this thing here, these are the things which tell you about the distribution of the polymer. And remember, we talked about the idea that the polymer, the thing formed with the polymer, that's going to be related to our refractive index. Okay, so this here, this is the thing that's going to tell us about the refractive index modulation, and this will tell us about any average index effect that happens. Again, this is a physical model, and we're talking about the production of polymer being related to the actual refractive index modulation. It's an assumption. Well, first of all, we can come along and we look here just at the solid. Forget the dashed lines for the moment. We look here at the solid lines. And what we see here is as the exposure time here increases, this dose increases, what we will see is that for certain parameter values, here we've got a visibility which is 1. We've assumed the diffusion doesn't change with time. And we've got this R parameter here, which is, as I said, important thing. This R parameter down here, which is this lumped parameter, tells us this type of information. So it's basically telling us information about how much diffusion is taking place and how much polymerization is taking place. We can see that, and this is very typical, that the average amount of monomer decreases with time. We're churning the monomer into polymer. So over time, the average amount of monomer is decreasing. And what we see is that the first harmonic of monomer has a negative value, and it's going to increase and then decrease. So the first question is, how come the first harmonic is negative? And the reason is because, as we said, we have an exposing pattern where in the bright regions we're taking away monomer, and in the dark regions we therefore have more monomer. And so what happens is when we switch the light on, we're going to not be increasing the amount of monomer in the dark regions, but we're not going to be using up monomer. So we end up with a cosinusoidal monomer concentration, which is exactly out of phase with our cosinusoidal illumination and cosinusoidal polymer distribution. So it's out of phase. So if we have a cosine for the actual polymer or for the light, we're going to have minus the cosine associated with the monomer. And so we have a negative sign. And we can go and we can look at the higher harmonics as well. And we see that we actually produce a higher harmonic, and this is actually positive. But the size is much smaller. This here is 2, this goes to minus 20, and this is 100. So we start off at 100 and we decrease down to 0. Now, as this is happening, we're producing polymer. And what's going to happen with our concentrations of the polymer? Well, a couple of things are going to happen. One thing that's going to happen is we're going to see a change in the average monomer concentration. So this is the average monomer concentration is going to increase. We're going to get a formation of a DC component. And we're also going to get a production of our harmonic. So again, just look at the solid lines here, of the harmonic. And we're going to get an N2. And what we can do is we can say, well, let this exposure here increase here. We say, in fact, 10. So we increase out here to 10. So we find out what is the maximum we get. When all the monomer has been converted into polymer, what happens? What's the maximum value we get? So we have used up all the monomer. And here again, we've obeyed a certain set of things, and this is tied in with this R value. We've set our exposure and our polymerization rate and our diffusion rate up so that all the monomer can travel from the dark regions into the bright regions, and they can travel in nice and smoothly so that I record quite a good sinusoidal grating, but I still have some higher harmonics. I'm still going to produce some higher harmonics. So we haven't got a perfect sinusoid formed. We've got at least a DC, a first and a second. We've got some non-uniformity in our cross-sectional refractive index modulation. Now, an important point is what happens if we let the time or the dose go to infinity, and we change the period of the exposure. We change the period of the exposure and we examine our R parameter. Where we can go and we can look at what happens to these values as we change this R parameter, which, as I said, quantifies how the monomer moves from the dark region to the bright region, and also the rate at which you're removing the monomer. And we get something which looks like this curve here, where we see that when the R parameter here is small, so that would correspond to a very high rate of polymerization, or a small value of K, and a small value of K means a big period, because the K, remember, is proportional to 2 pi, or is equal to 2 pi over the period, so it's inversely proportional to the period. And here we've got a square, so we got 1 over the period squared. And what we see is when we do that is that we have a significant drop off in the value of N1 as we go to smaller periods. We get a significant drop off as a function of R. As we go to this, yeah. And so and if we increase this F0, we also get a drop off. Meanwhile, as we come over here, yeah, so a situation where this K is very big, so this would correspond to a very small period, for example, or an F0 value which is very small, we get a very high N1 value. So what this is indicating is that this model tells us that if we make the period very big, we're not going to get a good modulation. But if we make the period very small, we're going to get a really great modulation. In fact, the bigger the smaller the period, the bigger the R value, the better the strength of this grating that we can achieve. Now, so we have here our monomer changing, we have our polymer concentration changing. What does our cross-sectional profile look like? Okay, so if we could imagine taking one period of this grating and plotting out the modulation. Again, if we look at the solid lines here. So this is n as a function of x for a particular time. And what we see is we got this, for an R value equal to 1, we get this formula here, and we see it's not perfectly sinusoidal. So we're putting in a sinusoidal intensity variation, but the result is not a sinusoidal modulation of the polymer density. If we increase R, if we make R much bigger, and again, how do we make R much bigger? Well, we reduce the rate of polymerization. We have a slow exposure. We have low intensity, long, slow exposure. Or we decrease the period. Again, if we decrease the period, R gets bigger. So we make the period smaller. Then what we see is we get something much, much more sinusoidal. Okay? So the bigger this R value, the more sinusoidal, the slower our exposure, the longer the time for monomer to diffuse in. We get something that's very, very sinusoidal. It's high fidelity. Whereas if we go to this R value of 1 here, we see that we lose this fidelity. We put in a sinusoidal variation, but we're not getting something sinusoidal out. We have a distortion. And in fact, if we take a very small value of R, we see that we have very high distortion. You can see this very high distortion here from this solid line. What do these mean for our actual diffraction efficiency? Well, if we take our modulation of polymer and we assume that the refractive index modulation is directly proportional to the first harmonic. So we neglect all higher order module, so N2, N3, N4. We just assume we have a nice single grating like Kogelnik talks about, and we assume that it's a thick grating, so we can use Kogelnik's expressions. And then we assume that our refractive index is directly proportional to N1, okay? We can plot out the resulting diffraction efficiency. So we multiply this by some constant and we put it in as the N1 value, and we get something which looks like this. And for this case here, we see that we get an overmodulation, again, the solid line, we get an overmodulation, and then we come down the other side. So we have a maximum diffraction efficiency here, which is equal to 1. If we had this experiment, we ran our experiment, we monitored our probe beam diffraction efficiency, we would see it goes to 1, and then basically, as we expose longer and get a stronger modulation, it's going to decrease. If we take this value of 50, and we see here we have a much higher fidelity, and if we look at the amplitude, we also see here 200, whereas this is 100, and the 200 here, again, we can think about the idea that we had started off at a concentration of like 100, and now all the monomer went from the dark regions to the bright regions. And so we produce this very, very strong polymer concentration in which we have a maximum here at 200. We've managed to basically take enough monomer from there to bring in here to go all the way up to 200, okay? So this gives us the strongest modulation. And if we look at our diffraction efficiency with the solid line, instead of coming up here and then dropping off, because we can make more polymer, and therefore we have a higher refractive index, much earlier we get a higher diffraction efficiency, 100% sooner, and then we overmodulate and come all the way down here. So in this case, because we've got higher fidelity, we've got a bigger R0 value, we can make a stronger grating, and we can get there more quickly. Similarly, in this case here, we've got the maximum distortion. We've got this sort of a growth curve that comes up here. It just about reaches 1, and then it drops off. Okay, it's a very, this R0 being very small means that our polymerization rate is very high, or our diffusion rate is very small. Okay, it's very slow process. So we still have monomer that can be coming in, slowly in and being exposed, but we also get this also being converted into higher harmonics. Okay. Now, I'm not going to show experimental results for this, they didn't, and I'm not going to bother. But what I'm going to tell you is that this model has advantages. And the advantages, I hope that you can see, it's pretty much physically appealing. It's got a very simple, solid physical base, driven diffusion process. It's got similar types of mathematics to Kogelnik. So if you can do Kogelnik, you can certainly do this, and it's easier to do than Kogelnik because we've got real values. So physical appealing, some insight, and nice to work with. And then the disadvantages. There's no photochemistry. We've not talked about any actual photochemistry. We just assumed constants and proportionality. We had this parameter kappa, yeah, if you recall our kappa parameter. And all we said was, we're going to have a polymerization, which is proportional to the intensity, and we're going to stick in a kappa constant, and that's going to tell us how we convert photons into, how photons are absorbed by dye, and how the dye goes through all these different processes and produces out the radical, and the radical initiates the polymer. That's it. All of that is lumped in here. So there's not much physical insight here at all. But again, if it gives us a first idea. There's no polymer science. There's no discussion at all about the processes we talked about above in the figure, where we have this conversion of the growing chain eating up monomer. There's no description of that. Or does the polymer move? Does it diffuse? Short chains will move. There's no real description, very simple description of the monomer. If we want the monomer, at least we've said, well, it can diffuse, and we've said maybe the rate at which it diffuses will change because of densification, but that's pretty much it. Okay, so there's quite big drawbacks. Yeah, there's the relationship between the material and the refractive index is very simply modeled again. All we've said is we have a polymer concentration, and we can multiply that polymer concentration by a constant, and that gives us our refractive index. It tells us nothing about the actual refractive indices of the materials in the actual layer. So monomer will have a refractive index. The polymer and the different length chained polymer, each one of those is going to have some slightly different change in refractive index. Okay, so all of these things, and even the dye is going to have some refractive index. There's no discussion about how any of these things contribute to the refractive index value of the grating. So again, it does give an accurate physical prediction. As the period increases, K decreases and R decreases, and the modulation decreases. Okay, why? Because the monomer cannot diffuse quickly the long distance into the exposed regions, and so you get distortions. You don't get a nice sinusoid, you get a distorted sinusoid because of the fact the monomer has to travel, and you can basically end up with saturation effects. But there's one prediction it makes which is very inaccurate. Okay, as the period decreases, K increases and R increases, and the modulation increases. That's the prediction of this model. The monomer in that case has only got a short distance to diffuse from the dark band to the bright band. So the smaller the period, the less distance the monomer has to travel in order to get into the bright band. And so effectively you get to use as much of the monomer as you want, and you want to have a nice sinusoidal result. So the monomer gets quickly in there, and you can use up all the monomer, and you make a very nice sinusoid. So the smaller the period, this model says, the better the high spatial frequency response. There's no high spatial frequency cutoff effectively. The smaller the period, the better it gets. Okay, and that's clearly wrong, because if you get the interference pattern smaller and smaller and smaller, eventually it's going to be smaller than the size of the monomers or the polymers, and so it just won't work. So it's not fit. And every material you know has got a resolution. And so there's no scaling here. There's no scale parameters in terms of resolution. So the photopolymerization driven diffusion model, and applied, for example, to free radical like acrylamide with PVI, as the intensity increases, yeah, so our intensity of our exposing pattern increases, the rate of polymerization increases, and R decreases. As the period increases, the K decreases and the R decreases. Therefore, the lower the illumination intensity, the longer the exposure, and the finer the fringe period, the larger the R and the better the profile. It's better in terms of its modulation size, and it's also better in terms of its fidelity. It's more like a single sinusoidal recording. And that's the first model. Okay. The second model is then something I proposed back in 2000. And again, it's been out there long enough for everybody to pick holes in it and me to pick holes in it and make them better and better. So I think it's quite a reasonable place to teach. It's something reasonable to teach to graduate students. In this case, we're going to assume that the chains are not localized. Okay, so where we put light in and we start a chain is not where that chain is going to grow, or specifically not where it's going to always remove monomer. The chains grow away from initiation points removing monomer at positions away from and at times after the place and time of initiation. Okay, so we got a figure. What does this look like? Well, here's our experimental system. We've got our two exposing beams and we've got a ray play beam, the probe beam. And we've got a bright band and a dark band. And we're going to get monomer diffusion from the dark bands into the bright bands. So this, up to that point, we're pretty much talking about the PDD, photopolymerization driven diffusion. Okay, but now what we're going to say is that inside here we're going to have polymerization, and the polymerization has the following basic sets of characteristics. We're going to get a point at which we have initiation. That's the point at which a photon is absorbed by the dye, and the dye generates this radical, and the radical starts off this chain formation process. Okay, and each one of these dots we could imagine is a particular monomer molecule, and that monomer particle has been used up at some position and at some time after this initiation. So there's a time lag. If, for example, I put light in and I start the chain growing, and then I switch the light off, even if I switch the light off, this chemical process of chain growth will not necessarily stop. It's going to keep going for some time. And if we've got millions of these chains growing, what we're going to see is that over time, the millions are going to become hundreds of thousands, are going to be tens of thousands, etc. Yeah, it will decrease with time, but this process will continue. And since we're associating polymerization with the refractive index, we will see the refractive index evolving after we switch the light off. And therefore, we will see the probe beam diffraction efficiency continuing to change after we switch the light off. And we can talk about that as being non-local in time. These dark effects, yeah, as being non-locality in time. Things happen after this initiation process. But we also have, and it turns out to the first approximation, it's more important, we also have this non-locality in position. We start this process and we remove a monomer over here, but over time we're removing monomer at points displaced from the initiation point. So if we can imagine putting a sinusoidal intensity pattern in there, what this is going to mean is that this is removing monomer some point away from the initiation point. So we're going to get a smearing of the actual sinusoidal pattern. So even if we have an R value, which is very big, very big. And so we've said from the PDD, we're going to get a very smooth response, very nice sinusoidal pattern. As we make the period smaller and smaller, the probability that we can start growing a chain here, and that chain is going to grow into the dark region. So we'll get polymerization in the dark region due to the growth of chains from the two adjoining bright regions. It's going to increase as the period gets smaller, until eventually, if the period is very, very small, we're going to get chains growing all the way from one bright region through a dark region into another bright region and even into another dark region. So we're going to smear out the effect of the actual grating formation. We're going to have the production of average index as opposed to the periodic modulation. So we'll reduce the visibility of the actual refractive index formed. Instead of having a strong modulation, we'll have a stronger DC and a weaker modulation. So we have initiation of the chain, we have propagation or growth of the chain, and then we have a termination process. And it turns out that in fact, the initiation involves the dye, propagation is polymer, and then we have a termination process. And there are very different types of termination process. We can have long chains terminating long chains. We can have long chains terminated by short chains or single radicals, and we can have other types of termination process. And how we actually deal with those also affects the results we get. Okay, so mathematically, we do exactly the same thing as before. We assume that we're going to have a polymerization rate, which is this constant F0 times this. So effectively, it's simply going to be some material constant times the intensity. And again, we have the V, and we'll take V equal to 1, and we've got 2 pi over the period, the K, the grating vector. But now we have a different governing equation. So we have the same first part here, the same fixed diffusion, which is associated with the diffusion of the monomer. But now we're going to be removing polymer, and we're going to remove polymer not just at a point, yeah, not just at a particular rate at a particular point, but we're going to allow for the smearing in time and also in position. We're going to allow for the fact that the chains grow in time and the chains also smear out in position. Now, the first thing we do is we say, well, let's assume that the time constants associated with this are very, very short, okay? So what we do is we assume that this process here takes place quickly, yeah? And therefore, we're going to neglect the non-locality in time. We're not going to worry about the dark field effects initially. In fact, what we're going to assume is that this or here can be replaced by a simple Gaussian type function, a smearing type function. And we refer to this here as our non-local function. So this is a generalized form, but we're going to neglect, we're going to basically assume that the time part is a delta function in time, okay? But there is a smearing effect. And that smearing effect is determined by this exponential, this Gaussian term. If you want, you can think about a filter, and you can think about the process of convolution in space. We can imagine having a sinusoidal variation, and then we move this filter across it and we smear it out in space. But of course, it's still part of a dynamic process because we still have monomer concentrations at particular points varying with time, and we have a polymerization rate, which may vary with time and with position. In our case, it's only going to vary with position. And we do note that in the limit, as this non-local parameter, this length scale, this is actually a square, yeah, it's length squared, yeah? As this varies with time, as this varies, yeah, or as we change the value, if we go to a local case, so we assume that we go from the non-local case here to the local case, so we let this smearing, this chain length effect go to 0, this becomes a delta function, and so we get right back again to our f times u that we had previously. So in the limit, we get right back to the PDD. So we can go from the non-local to the local. And so we can test the predictions, the numerics. Again, what do? Well, we assume Fourier series. Yeah, we come along and we assume Fourier series. Sorry, if you want to take a little break now, just for people to go to the bathroom and stuff like that, we could take a couple of minutes. And if you want to ask some questions, you could ask me some questions. Has anybody got any questions? No?
Yeah, here is a question from Andrei Viktorovich.
Okay.
Well, Professor Sheridan, my question is about non-locality.
Yeah.
As I remember, the idea of non-locality was also applied, it was applied not only to photopolymerizing systems, but also to that our material with phenantranquinone, which is only photochemically attaches without any chain process.
Sorry, can you just repeat that because it faded in and out there? Sorry. Just repeat the question.
Okay. So as I remember, the idea of non-locality was applied not only to photopolymerizing systems, but also to the material with phenantranquinone, which is not photopolymerizing.
Yes, the PQ-PMMA. Yes.
Yes. Yes.
Yeah.
So what is the physics of non-locality non-locality in space in that case?
So,
in your opinion?
So in that case, so we actually we went away and we came up with a list of potential sources of this smearing effect. Okay, this non-local effect, and basically anything that's going to produce the smearing can be modeled in this way. So, for example, in a real system, there's going to be some vibration. So if you have the actual plate vibrating relative to the exposing pattern, okay, or if you have the fringe pattern varying in any way with respect to the plate, so for example, frequency variations in the source, both of those will also produce this non-local type effect. Yeah.
Okay, I see. So it was a sort of empirical description.
Exactly.
In that case.
Yeah. And the point I would say is that how do we compare how can we compare the performance, the material performance of different types of systems if they have very, very different photochemistry? Well, what we've done is we've gone out and we've derived equations associated with the different materials. And sometimes these materials have very different photochemical processes. So for example, in PQ-PMMA, typically you expose it, and if you monitor it during exposure, you see very, very weak diffraction. But then you post-process by exposing with some light. And what you actually do is when you expose, you produce two opposing grating structures, and then you wipe out one of those by the post-exposure. Yeah, you've got two distributions of materials, one of which you remove. But we've used our model to explain that or to describe it. Yeah, but again, the same sets of parameters can be used. So the non-local parameter basically characterizes the cutoff associated with the highest spatial frequency achievable given a particular material in a particular experimental setup.
Okay, thank you. My idea was that the non-locality in that case was due to the diffusion of radical.
Oh, I mean, this is the thing. I mean, so we have seen that as well. And we looked at this diffusion of the radical. The point is, again, you can build that, you've got a lumped parameter like a black box, and you can throw into it any number of things. Okay, then you go away and you say, okay, now I'm going to study it in finer detail, and I'm going to describe or find the contributions, the finer detailed contributions to this parameter. And of course, in particular situations, having a simple linear parameter like sigma might not be a very good idea. You might want your sigma, your non-local parameter, to be a function of something. And that's certainly possible and certainly the case. Yeah. So it will vary, for example, as you change temperature. Okay. But again, the point here is that typically as an engineer, I've got some sort of process and I want to be able to characterize it for different types of materials. And at the end of the day, if I can compare, if I can do experiments that allow me to cross-compare the performance of different materials in a very simple way, then I'm happy. Yeah. I can then go away and I can find much more rigorous models associated with different systems. I'm going to present, hopefully I have some time, and I'll talk about the different parameters I see for different materials and for different dyes in particular. Yeah.
Okay, thank you. And as I remember, a typical value of that non-locality parameter in photopolymers was about some tens of nanometers, right?
Yeah. So for the acrylamide, and again, I've written papers where I've explicitly said the acrylamide is a bad material. So for that material, we've seen square root of sigma values, so lengths of 60 nanometers, things like that. If you go to the Covestro type material, you're getting down to about the 10 nanometers or sub 10 nanometers. In fact, in some cases, we saw 5 nanometers predictions for that non-local effect. Yeah.
Do you associate that those values with the size of macromolecules?
Now, that's a very interesting question, because the problem is, again, if you take your polymer growth and, so the sizes of these things are big, they're typically very big. You're talking about tens of thousands of monomers, okay? And so this can be thought of, sometimes I think of it as a big ball in space. And of course, you can then find out an effective radius for something like that. So an effective radius. So for me, I see the non-local parameter as being associated with this effective radius, which again, there's a statistical, you've got a spectrum of chain lengths, and therefore you're going to have some average radius of effect. And of course, these are growing inside a matrix. So there's a whole set of processes whereby radicals get trapped or the tips of monomers get trapped. So it becomes much more complicated. The people talk about cage effect. So these actual things, and there are models for these, but we've published papers with models of these things. But what you tend to find out is the models get more and more complicated, and you have more and more parameters that you essentially empirically derive. And so the question is, what are the, if you're not dealing with very specific materials and very specific problems, it's very hard to get a general picture. Okay, so as you said, PQ-PMMA, this non-local parameter results from a number of other effects which are not associated with chain growth, because there is no chain growth. Yeah, there's an affix, the PQ affixes to the matrix, the PMMA matrix. Yeah, and there may be some then motion of the MMA, for example. So it's I think maybe I'll just keep going now, because again, I'm trying to introduce this to the students, and what you're talking about, I can give you access to papers and stuff like this without too much
Yeah, I
difficulty.
know. Okay,
You know?
thank you very much.
And I certainly don't have the answers to everything. You know, this is complicated stuff. So again, we do like Kogelnik, and we have our monomer harmonics. So here's the 0th order, the DC, and here's our 1st order. And again, now we see that this non-locality, this e to the power of minus k squared, the sigma appears here. And we often write that down as an S parameter, the non-local effect parameter. Yeah, it's going to be a constant. It's going to go from, when sigma is 0, it's 1. And it's going to go, of course, as sigma increases, there's going to be an effect that this S is going to decrease from 1 to 0 as this sigma goes to infinity, okay? And we see it appears here, and we see it also appears here. So it's going to affect the coupling between the 1st order and these other components. So it reduces the coupling to the 0th, to the 1st order, and to the 2nd order. And we can then have a Fourier series expansion of our polymer concentration. And what we see again is that we have a non-local parameter appearing right here in the front of this integral, okay? So if we look at the N1 before, the only thing different is that we didn't have that parameter. So as the non-local parameter increases, we'll see a decrease in this 1st harmonic. That's the effect of decreasing the non-local parameter. And we also see here that we have k squared, 2 pi over the period squared. So we can see that we have, in fact, this non-local parameter, yeah, divided by the period squared. Yeah, so that non-local parameter divided by the period squared, yeah, depending on that value, we're going to be producing less of this. And since this is going to be directly related to our 1st order modulation, we'll see that we have a reduction, an effective reduction in the modulation, the refractive index modulation, produced by the use of this non-local parameter. The more non-local we are, or the smaller our period, because if we get a smaller period, we've got the sigma here divided by the period squared, this here is going to get bigger, and therefore this is going to get smaller. So the smaller the period, the smaller this gets, and the bigger this non-locality, and the more the chains grow, the smaller this gets. And so we can begin to see where this reduction in response at high spatial frequencies can come from, okay, mathematically. If we go and we look at our curves now, these are the same curves we had before. So the solid line here associated with completely local, and the dashed lines are the effects of non-locality. We've got 2 lengths here. We've got this equal to 1 over 64, okay? And we've got this here is 1 over 32, okay? So we have more, this is more non-local than this for a given period. And again, this is quite nice because we can look at results for all different ranges of periods. And what we see is that as this parameter here changes, as the non-locality gets bigger, we get a weaker monomer concentration difference, yeah? We see we get a weaker polymerization, and we see it just drops. This is just dropping. So as we increase our period, we're seeing the amount of monomer concentration here just drop. So this is perfectly local, non-local, and more non-local. And we can see similar effects for the higher monomer concentrations here. As the time goes to infinity, we see this type of effect here for the R. And again, our R parameter, we call the R parameter. So we're changing the R parameter, and we're seeing what happens when we have this non-locality. The sigma divided by the period squared is equal to this. And what we see is that this curve here decreases. We have a decrease in this curve. The saturation value, the maximum value of N1, yeah, decreases as we change R. We still have this very low value here, but what we see is that this here is moving in this direction. This R scale is moving in this direction. So again, and then we see here in the higher harmonics, it's a similar type of effect. So we get a drop off in the spatial frequency response. What do our cross-sectional permittivities look like, or sorry, permittivities, polymer concentrations look like? Well, again, this is our local case, yeah? And here for this R value of 50, we've got a beautiful sinusoid. And as we make the thing more and more non-local, we lose this N1 value. So the more non-local it is, we retain the same DC value, but the visibility of this interference pattern is weak. We've still got quite good visibility, and it's still quite sinusoidal. So we have a linear response, but we've lost response. If we go to 1, we see here that we've got the higher harmonics come in, and we still have some higher harmonics here. But as we increase the non-locality, we get higher fidelity. The higher harmonics are decreased more strongly than the lower harmonics, okay? And if we go back to our maths here, what we see here is we have a k squared here. If we go to n2, we end up with I times k squared. So 2, this would be a value of 4. So the higher harmonics are suppressed more, yeah? So if we have the second one, we're going to have 4 times k squared. If we go to the third one, we'll have 9 times k squared. So what that means is we get better fidelity the more non-local it is, the more we get, more sinusoidal it is, the more suppressed the higher harmonics are, yeah? But of course, if we go to an R value, which is very small, yeah? So again, remember what that means. It's very hard for the monomer to diffuse out. We're using up the monomer very quickly. We've got a large gradient maybe, but we don't have, for example, the ability of the monomer to get into the bright regions. We still have an improvement in the fidelity. The result looks more sinusoidal, but we also have a significant decrease in the actual grating modulation. And again, if we come over here, we see again the fact that in this case, the non-locality means we don't get overmodulation. We don't go up and come down again. We don't achieve that strength. And here, we've got a perfect sinusoid. We do get overmodulation, but you see this overmodulation here, this type of behavior, we go up, but we don't come all the way down. And again, in this case, we see the steady decrease, a steady decrease in the achievable diffraction efficiencies, because we're not getting strong gratings and we're not able to achieve the same level of overmodulation. Those are the general characteristics. And so we see we can get quite accurate fits to our growth curves, and we can, for high spatial frequencies here, this is typically, this is 2000, an R15 and an S, so this would be parameters we placed in to get a good quality fit. And we see the quality of the fit in the lower values down here, where the effects associated with the dye are more significant, and we haven't really modeled the effects due to the dye very well. The fit isn't as good, but as we go up here, it gets better. And if we take this acrylamide and we go away and we find out what the spatial frequency response is, we can definitely see that experimentally we have a reduction in the spatial frequency response as we go to these higher spatial frequencies. Now, we haven't looked here in this case at the low spatial frequencies. We do this in other places, but we can also see there'll be a drop off over here. So the drop off for the lower spatial frequencies is well described by the PDD, but the PDD would say a good fit, and then it would go simply straight across here. It will be completely flat. But experimentally, we see low, and then it goes up, and we have a band here where it's very linear, very good response, and then it decreases down the other side for higher spatial frequencies. And I think I've shown you a graph before with the covestro. Just I pop back up here for a second, just to remind you of this, because it's quite nice to see, I think. Come on, sorry, it's right up here. Here, yeah, where we saw this is the type of response we get here for the acrylamide, and if you look at this, you can see it ties into the result I've just shown you. But and it drops for low spatial frequencies. The covestro also drops for the low spatial frequencies for the very big periods because of restrictions due to diffusion, rates of diffusion. But it carries up here and it gets better and better and gets stronger as we come up here, and it only begins to drop at 5,000 lines. So it's a better material, you know. And the main reason it's better is because it's mass produced and they guarantee a certain quality or standard of production. Okay, so we talked about the PDD and now the MPD. We've looked at the general characteristics and we've seen that we can fit experimental curves reasonably well. We can now do this and we can talk about the comparison. The NPDD for the acrylamide PVA, as I0 increases, the F0 increases and the R decreases. As the period increases, the K decreases and the R decreases, so that will explain our low spatial frequency cutoff. Therefore, the lower the illumination intensity, the longer the exposure, and the finer the period fringe, the larger R, and so the better the profile. But with our non-local case, now we've got some additional things we can say. We can say that as the period decreases, K squared sigma increases, and delta N, which is a constant time times N1, decreases, and the first order grating is suppressed. So we don't get as strong a modulation because of the non-locality if the period decreases. So we have a finer period. We have a higher spatial frequency. And as the period decreases, an integer times k squared times that increases more rapidly. So for higher order, here's for n1. Now we're talking about n2, n3, n4, nm. Yeah. And so the delta m, the modulation of the mth component, which we say is a constant times this, decreases, and it decreases square of m. And the higher order grating components are even more heavily suppressed. Okay. And therefore we have more sinusoidal behavior from the grating. Yeah, we effectively filter out the higher order grating components. So the non-locality has the effect of making our recorder grating purer, okay, making it purer, okay. So, for our case, we can compare the PDD and the NPD. So again, we have the physically appealing, similar mathematics to Kogelnik. We still, however, have no photochemistry. Yeah, the effects of the photosensitizer, very simply modeled. We simply have a direct proportionality. We have no polymer science. We've not really talked about the polymer science beyond this sort of a vague idea that we have this chain growth. And the relationship between the material and the refractive index is very simply modeled. But we can accurately talk about the low spatial frequency cutoff, depending on this R parameter, which was in the PDD. And now we can accurately predict that as the period decreases, the K increases, the R increases, and the modulation no longer increases. We now predict the high spatial frequency cutoff. Okay, so we've got this other thing that's very important. Okay, now I'm going to talk a little bit about the adjusted PDD, but I'm not going to talk a lot about this because I still am happy with some of the ways I've described this, but I'm going to talk a little bit about it just to give you a taster. And then we'll finish maybe a little bit earlier today than before because I've got a lecture at 10, which I need a few minutes to get ready for. So we're talking about adjusting the NPDD in some way. The process of chain initiation involves some nonlinear effects. So before we said our rate of polymerization is simply proportional to the intensity. What we're going to show is that to a first order, it's more true to say that it's proportional to the square root of intensity. Okay, so again, what's our processes? And these are the chemical type of formulas. We have an intensity, we have production of radical. In fact, we produce two radicals. And this depends on our dye, and there's going to be a lot more discussion about this later. But so far, all we've done is we've said, look, the radicals are produced proportionally to the intensity. The radical interacts with the monomer, and that produces a radicalized, an initiator, a radicalized monomer, and it does that with some rate, okay? So there's a rate, and there's also a rate associated with the absorption of the intensity. You then have the propagation, and the propagation involves this radical interacting with a monomer to produce a certain length of polymer chain with a radical on it. And typically, we don't individually look at the progression of each chain. Now, you can do this, but it turns out to be fairly numerically intensive. And we've done a little bit about it, but it very rapidly descends into, because you've got, at the end of the day, the argument would be that because you have so many chains and so many chains growing, and the process is relatively linear, certainly in the early stages, that you can treat the whole thing as a bulk object, a bulk effect, okay? So you can just work with averages. But this is our propagation process, and we need to be aware of that. Then we have termination processes. And again, how we model this is, there's various ways to model this. But we can have two long chains coming together, or we can have, and forming a longer chain, or two chains coming together and just the tips act to sort of produce something like this. So two chains independently, but no longer growing. Or we can have one of the radicals interact with a growing chain and produce dead polymer. So the general term is dead polymer, chains that are no longer growing. Another process, we're going to talk about this idea of inhibition, where we can have a molecule, some sort of oxygen typically is assumed, interacting with a radical, one of these radicals, to produce something like this, which is a scavenged radical. It removes basically the radical. The radical is no longer available to cause an initiation process. So it's no longer available to initiate a chain, to radicalize a monomer. And you can also have interactions as follows, where you get with a different rate, and you can basically produce something like this. So the oxygen or the inhibitor acts with their growing chain to produce dead polymer. And you end up with dead polymer, either two independent molecules, so this is now radicalized, or you end up with something which looks like this. So you end up with a dead polymer. Now, there are so many different variations on these. You can read books about types of monomer that you need two radicals to kill them, or the chain growth, or they attach to the matrix. There's a lot of different processes, but again, it's trying to distinguish which are the most important. So for example, if you find out that this is more important than this, or if you find out that this is the more important process. And what generally tends to happen is you find out that this process is more important at different parts. So when you've got lots of radicals, this seems to happen. And on the other hand, when you've got lots of long chains, this basically is what happens, or you have no reaction at all. You simply have one of these growing chains. There's no monomer available, and basically becomes dead by itself. Through some thermal action or interaction with the matrix, it just loses its charge, if you want, okay? So this is just to give you a bit of a scare. But again, it's to try and say, look, what are the type of processes that are happening? So this is fairly dense, and often what people will do is they'll produce a diagram like this in different parts or steps. But I'm going to jump in here a little bit because we're going to meet the various subsections of this as we go forward. Here's our, we've already seen some figures like this, but here's our dye, and the dye absorbs a photon to produce a singlet state, okay? And then through what's called inter-system crossing, yeah, we can produce a radicalized dye. And I can give you the paper with all these various equations and references, which are differential equations. And this is the one that's important for the initiation process. This is the thing that interacts with this electron donor in order to produce the monomer radical that we've just seen. Before we get out of this loop here, however, yeah, and here is our general initiation process, and this here will be our photochemistry. We can have various processes by which we emit light and get to the ground state, or we interact with the electron donor to go to the ground state, or the triplet state here is going to have some molecular collision, okay, and go back to the ground state directly, or it's going to interact with some sort of an oxygen to go back to the ground state, or it gives out electromagnetic energy and goes back to the ground state. And there are, as I said here, there are equations, references, or there's equations where all of these things are discussed. Yeah, and I can give you the key for this of the paper I took this out of. Once we're down to this ground state, we can then interact, for example, with free protons. And these are byproducts of other chemical reactions that are happening in the material. And this can lead to the production of this LICO dye state, and hopefully we'll have time to talk a little bit about this. Or we can come down here and we can go into this excite. This is the radical that we had R for. And this will give out, this process of the radicalization gives out this proton, which can be used to produce the LICO state. And that gives us an interaction here, which is going to give us either bleaching to a dihydro state or production of the radical monomer. Once you've got the radical monomer, you're still not out of the woods, because you can still have inhibition. You can have radical inhibition as shown up here, or you can have inhibition with the interaction of the inhibitor with the actual radical, this initial monomer, just to kill it dead. And all of these processes here basically stop the reaction. You don't get any formation of polymer. And so this is part of this process where you're illuminating with light and nothing is happening inside your material. And again, now this is for a free radical material. But once we've got this radical and monomer, we can start to grow our chains. Okay, so this is our propagation step. And the propagation step terminates through those various mechanisms I just talked about, where we have a dead chain, we have two long chains, we have a termination with a radical, or we have a combination where we have an even longer chain. And again, there's references and discussions, we've done papers about all of these different processes. Now, the thing is that every one of these lines feeding over here, these productions, all of those things are governed by rate equations. You can write down the chemical formula for them, and we can write down at least a first order differential equation governing that process with a specific rate associated with it. So you can see that very quickly, and this is, I have to tell you, this is actually quite a simple system, okay? This is actually quite a simple system, okay? But we'd have, as part of it, a set of coupled equations just dealing with the dye, and a set of experiments to find out as much as we can about these processes associated with the dye. And then a set of equations governing this process down here, this initiation process and chain growth, with different types of termination inhibition algorithms. And again, we'd have specialist experiments just to find out about inhibition, and we'd have some experiments to try and find out about termination. Okay, and simple experiments, because again, the point is we want to do all of these experiments using active layers. We don't want to be dealing with these things by themselves. We want to be dealing with them in an active layer, a layer that's as true to or as close to the actual layer we're going to be doing exposure in. Okay, I'm going to stop there really. Maybe I just introduce a little bit of the notation here that I've used, so far I used U, the parameter U, to talk about this fixed diffusion law. And but a more standard notation, and this is part of the process of writing the papers in our work, has been trying to come up with a notation that other people will understand. And this is a difficulty because, as I said to you, the chemists use very different notation. Yeah. And so what they tend, when they have concentrations, they tend to use a square bracket. And for the monomer, there's a tendency to use this capital value M, okay, in the literature. So this here will be the PDD model written using that notation. And this here would be our polymer. Yeah. So before we just had this N1, we had the capital N. There tends to be the use of this capital P. And again, the square brackets indicating that this is a concentration. So this is the integral over from 0 to T, the exposure time of this parameter here. And again, there tends to be not the use of this idea of a dose. And as you go to the more nonlinear effects in the medium, because you have a generation which is proportional to the square root of the intensity, you can no longer talk about a straightforward dose. So the dose usually refers to the exposing intensity multiplied by time. But when we come to the polymerization, discussing polymerization, we no longer have a parameter which is just the intensity multiplied by time. We end up with the intensity to some power multiplied by time. So we don't have the same simple relationship with dose, okay? So again, we have an exposing intensity and we have a visibility, okay? And again, we have our monomer concentration as a Fourier series, and we often express that this is expanding out this diffusion term. So we have the diffusion term is related to the initial monomer diffusion rate. We have some decrease in the diffusion, and we characterize that as being associated with the amount of polymerization. So the polymerization rate appears here, and we have it multiplied by time. So it's telling us about the amount of polymerization, because the greater the amount of polymerization, the greater the densification we're going to have. And we have some general parameter alpha, which is just telling us about the decrease. And then we have this visibility of the fringes in the material. And of course, our parameter here, so the K is equal to 2 pi. So this was some of the difficulty I've been having with these fringes. So we now talk about this rate. Kwan from Korea talked about this idea that, well, we cannot treat this rate of change of monomer with respect to time in the simple way we've been talking about it. We've got to talk about it as being associated with some constant times the actual monomer, concentration of monomer, times this macro radical. So this now represents effectively all the chains that are growing. It's a concentration of growing chains. It doesn't refer to the actual length of the individual chains. It's all the chains that are growing. So this rate of change of monomer is going to be proportional to the product of the monomer concentration at a particular point in time, multiplied by the concentration of growing polymers at the same point in time. Okay? So this rate of change is equal to this. And the steady state condition, yeah, where the rates of initiation and termination, yeah, are equal. So we've got the same number of chains been initiated as terminated. And so this would be, we've started exposing, we've got some fluctuations at the beginning, but eventually we're going to assume that we've got as many chains being formed as being terminated, and that's going to run for some period of time. And then of course at the end, that's going to fall off as we have less and less monomer. Okay, so initially that's not going to be steady state, and at the end it's not going to be steady state, but in somewhere in between we're going to have some termination rate, and it's going to be associated, it's going to be equal to, it's a trick really essentially at the end of the day, but it's valid in terms of polymer science. An analytic solution to polymerization rate what can be obtained, which looks something like this, where I or I is proportional to I0 with some nonlinear parameter typically raised to the power of a half. So we have some polymerization rate, which is associated with the monomer concentration, and some initiation polymerization, all this raised to the power of a half. So I'll talk a little bit more about this the next day. In the non-local polymerization, in this notation, we have this equation now where we have this term, and I've tended to use this G here as the non-local form, and this tells you the total amount that's been polymerized. Again, we have a polymerization, we have the monomer concentration, and we've got this non-local parameter, and it's the spatial term. And so our amount of polymer is equal to that. That's our power. That's our sort of polymer concentration, okay? And then we assume that our refractive index modulation is proportional to that. We have a constant. And we assume that this here can be well written in terms of concentrations, amplitude components times the cosine ik, okay? So we have this development of the model. And the first one here is what Quan said. And he said basically, look, we're going to replace this here, yeah? This we had, our polymerization rate was simply equal to F0 times this, and we had the gamma here equal to 1. We're now going to replace this by a factor of 1/2. Okay, so we no longer have proportionality to the actual intensity. We've got a proportionality to the square root of the intensity. And again, you can think here, you're going from an intensity to a field or a field amplitude. So it's not a huge jump, but again, it's not that simple because it's mediated by all these chemical effects. As a result, monomer distribution, the monomer then is going to vary the diffusion rate. We've got the varying, which looks like this. Yeah. And again, this is more complicated than before. And it's more complicated before because we now have this polymerization rate. Remember, we said the diffusion is going to depend on the polymerization rate. But now it's more complicated because we got these factors of 1/2. So the variation of the diffusion as time goes by will be more complicated. But again, I write this out and it can be included, but it actually isn't awfully important because typically the changes in the diffusion aren't massive. We also note that we've retained this visibility function here. And of course, as the visibility goes to 1, for example, this will disappear and this becomes the square root of 2. Okay, so things simplify a great deal if the visibility is 1. So our model 1, we have this gamma is equal to 1, the linear one, and gamma is equal to 1/2 is the adjusted one. And you can compare and examine what happens as you change this function. And as you can see, it's going to have a significant variation, okay? So we can talk about X-rate equations. So I'm going to stop there now. It's 9:45. As I said, I've got another lecture and I'm going to come on and I'm going to talk a little bit about this. But what we're going to see is as we go forward with these different equations, we're going to get closer and closer to actually the rate equations associated with a range of chemical reactions. So we're going to get more and more physical. And I don't know if I've got anything I just want to mention in here quickly. Well, this then leads into this idea of holes. Okay, but I'm not sure if I'll take that as the next point. Okay, folks, are there any quick questions? It's 9:15 now. So if we got any questions about this description I've got up here. I'm sorry now, but as I said to you, the point is the notation, we're going to need to change notation because we've got to take a greater number of effects into account. And the U, it turns out, leads to confusion in the literature. So do we have any questions?
I see no questions so far.
Okay, very good. So I said no. Yeah, I'll as I said to you now, I give the talk on Friday. And if you want, I can give a talk on the Saturday, depending on how far we get and what people want to do. Okay?
Okay, Professor Sheridan. Yeah, actually about that, as you remember, we have a kind of a consultation on Saturday that we planned to be.
Okay.
And in the previous week, we discussed to cancel the lecture on Saturday.
Yeah.
And the students say that they prefer to have the lecture on Saturday, but to have one additional consultation, which we planned on Friday, actually.
Okay.
So if there is a need to take one other lecture, I can propose the following. Right now, I'll share my screen.
Sorry, no, I'm sorry. Just to be clear now, Vladimir. So so there's going to be no lecture on Saturday.
I guess so. Yeah. Yeah, I guess so.
So there's only one more lecture slot, which is Friday, and that's going to be a consultation where the students get to ask questions.
Actually, I have an option, and I want to say it to you. And for that, I will share my screen right now. Okay. So here is our schedule.
Yep.
And what we wanted to do is we wanted to make this one on the 4th of December another consultation.
Okay.
But what I propose is to make it as a lecture, is to stay it as a lecture.
Okay.
But then make 2 consultations. First one on the Saturday.
Yeah.
And 5th of December. It will be consultation on your lectures when the students can ask you questions.
Okay.
And the second consultation is pre-exam consultation on the 7th of December, and the 8th of December will be the exam. How do you feel about that?
That sounds fine to me. Yeah. So just to be clear, the 5th is the Saturday.
Yep.
So the 5th is the Saturday. Sorry, I'm getting very confused. I'm very sorry. Apologies.
So it will be like that. Right now, I'm rewriting it.
So today is the 2nd, and tomorrow is the 3rd.
Yeah, and we do not have any lectures on the 3rd of December.
And so we will have a lecture on the 4th.
Yep.
Correct. So the 4th is the Friday, and so I will give a lecture on the 4th, and then we will have consultation on the 5th. So I will be available, and the students can ask questions on the 5th.
Yep.
And then we will have another consultation on the 7th.
Yep.
Again, the students can ask questions. Is that correct?
Yep.
And then on the 8th, we will have the exam.
Yep.
Okay. And how will we be able to do all of the students on the 8th in that time slot?
I will ask them. Okay. So this is only a proposal. So yes, if you agree on that, I can ask to the students.
Sure. Sure. That's fine. And I mean, if we have to spend longer, I don't mind. It's just that if I know, then I put it in my calendar. Okay. Okay. That sounds good to me. Yeah. Okay. That sounds very good. Okay. And maybe you'll just send an email to remind people, and then basically, but also it would be very good if they could get the YouTube videos, and I will send them out the lecture slides from today and from Friday as soon as I can. Okay. Okay, Vladimir, it all sounds good to me. Okay.
Fine. Then have a nice lecture, I guess, and good day to you.
I must run away now. Okay. I see you guys. Ciao, ciao.